Greetings, everyone. Welcome to the AI Files, your ultimate destination for staying updated on all things artificial intelligence. We dive into the latest developments in the AI world, sharing insights from the corporate landscape. We also bring on expert guests to provide their unique perspective. You can find us in Apple Podcasts as well as YouTube channels. If you're serious about keeping up with the fast paced world of AI and want to integrate its advancements into your career and the company, then this is a podcast for you. I'm Shadab Hussain, co host of the AI Files. I'm the director of data and AI at Microsoft with over 22 years of experience in the analytics and AI field.
And I'm Jamie Basilico, co host of the AI Files. As a data and AI technical specialist and architect, I bring over 35 years of expertise in data related and AI domains, having worked with many of the Fortune 500 companies throughout my career. Please note, this is not an official Microsoft channel. The views and opinions expressed by the co host are their own and do not represent the views of Microsoft. So let's dive into today's episode. And I do want to bring back a guest that we had on previously, Simon Lacasse. He's a global black belt of AI at Microsoft. And we're going to bring him back in to kind of continue our discussion that we had with Simon around large language models. So with that, welcome Simon to the stage.
Hi, Simon. Thanks for coming back.
Hey, good to see you again, Simon.
Thank you for having me.
Okay, so Simon, since we spoke last time, there has been lots of questions. Everything that you told us about, everybody has a little bit more of the question. They want more clarity. They have some aspect which we could not cover last time. This topic can be actually so deep. And that's why we want to do this part two. So thank you for coming back. And we want to actually get started with some basic stuff. And then we'll talk about some of the advanced stuff again. But that's what we want to do in the part two.
Okay, sounds good.
Okay, great. Now, we talked last time about the large language models and you told us about how it works, but I just want to step back and ask you some very basic stuff. What exactly is a token and why the models predict tokens? Why can't they predict words? Why do we have to get down to the granularity of tokens?
Okay, well, ultimately, a token is fundamentally a unit of text that the model processes. And the process of breaking down text into tokens is known as tokenization. Let me, if you don't mind, let me share a quick slide just to kind of go over a little bit of the transformer model architecture and how tokens work and vectorization, because I think it's very important when we talk about tokens in general.
That would be awesome. Yes.
Okay, so what you see here is a very high-level diagram of a transformer model architecture. And in this diagram, what you can see here, typically, when you train these really large language models, they're trained on a lot of data, right? So what you see here is the data, and there's known sources of data that these models have been trained on, like Common Crawl, web text, Wikipedia. But what happens is that this data it gets transformed into tokens, and we'll talk about that a little bit later. But essentially, a token represents oftentimes about 4 characters, and from there, these tokens get transformed into these numerical vectors, and this is basically what the model uses to train the model. And then when they get transferred into these vectors, there's a few mechanisms that are part of the transformer model architecture, such as self-attention and positional encoding, that uses these vectors to be able to essentially encode this and then create this latent space that basically creates this kind of map or relationships of these words and how semantically correlated they are to each other. So for example, a cat or a dog would be very close to each other, right? And this is represented through numerical values that are vectors that were words that were transformed into tokens. Now, let me stop sharing my screen and we'll talk a little bit about why we use tokens for these LLMs. So going back to the question, why do we not use words or syllables, for the model? Well, essentially, tokens are more efficient. They allow text to be more compact. Tokens are also much more flexible. It gives the LLM the ability to deal with a broader range of words, and the tokenization process actually allows the model to understand the building blocks of words. And more importantly, tokens help the model capture contextual relationships between words. So let me use an analogy so you better understand. Imagine you're making, a fruit salad. And instead of throwing, all the fruits into a bowl, you chop them up into these smaller bite-sized pieces. And this way, it makes the fruit salad much easier to mix and eat, and to consume. So in the world of language, a token is like one of those bite-sized pieces of fruits, right? And when a computer tries to understand and generate language, it's like making a fruit salad. So the computer actually needs to chop up the sentences into smaller parts, which we call tokens. And these tokens can be words like apple, but they can also be parts of a word like app and ul, right? Like apple could be split up into two pieces. And I guess the question then becomes, well, why would you not just use a whole word? Well, sometimes you encounter, a really big fruit like a watermelon, right? And if you only use whole fruits in your salad, the watermelon would be too big to handle. So by chopping it up, you can manage it really easily. And similarly, by using tokens, computers can handle much longer and complex word by breaking them down into really smaller pieces that are like manageable pieces that the model can consume. Does that?
I really like that analogy that you just used, because that makes more sense, because I never thought about it in that way. It's like you said, if I try to put a whole watermelon into my salad, it's going to take up everything, and it's going to be hard to maneuver around that.
Right.
So, I mean, I've got a question for you, and maybe it dovetails into that. I mean, a lot of times we hear everything around context windows with these models. So I'm assuming there's some connection between tokens and context windows. So like, what is the context window? What does it really mean as it relates to, how big are those windows? What can you fit into it? And why aren't they unlimited? And does that in some way correlate to like your watermelon analogy?
Yeah, absolutely. I think they're highly correlated. So the context window, it refers to the amount of text that the models can process at one time. Okay, and this is measured in tokens, so which can be words or parts of word, right? Like we just mentioned. In a typical kind of retrieval augmentation generation scenario, the context window is used to insert new information to the model to reason over during that process. So the size of the context window actually can vary significantly depending on the model's design. So for some models, they might have very small context windows, like 500 token limits, while others might handle thousands or millions of tokens in the context window. And we get that question a lot. And the context windows, they're not unlimited. And that's because of the computational constraints that these models need to operate on. Processing, really large number of tokens requires more memory, and it requires more computational power. And this limit is directly correlated to actually the transformer model architecture that I showed before, and how tokenization, vectorization, and other elements of the architectures are implemented. So in other words, the model's architecture and the compute that it runs under directly defines the context window size that's available to that specific model. So in summary, the context window is basically a balance between the model's capabilities and the practical limitations of the model's computational resources and model architecture.
So is that why like the context windows are not unlimited then? Because it's bound by the
the architecture and the processing power of the model. Correct.
Got it.
Now, with that said, in the last year, researchers have worked pretty hard to increase these context windows while there's a balance that needs to be done when you change these models architecture and you try to increase the context window. You need to keep the efficiency of the model, but also keep the performance of these models and the relevancy of these models' output. Like a model like GPT-4 today has about 128K context window, and some other models have millions of token context window, but ultimately the architecture and the compute that's underneath that is very different.
Hmm.
So,
And
so how does that?
sorry, Jimmy. Tokens is very, very interesting to me, and I have some follow-up things on that token thing. Um, so it makes sense what you said, that okay, it's about the granularity, right? Bringing it more granular so that the models can process it better. Um, but when it's trying to interpret the prompts, um, the token is kind of in, I would say, it's unprocessable unit, because it can't really make sense out of it, right? It's kind of a gibberish. Ultimately, it needs to understand the whole word to really understand the semantic purpose of it and put that into that vector quadrant that you say, right? Who is it near to? Ultimately, it needs to assemble the word back from those tokens, right? So why the tokens are important. I've been thinking about it, and I realized that also the languages are different. So some languages have really, really long words, some have shorter. So tokenization helps the granularity. It brings all the different languages processing at the same level, so you can measure them commercially and process wise, and all that makes sense. Um, but to process them really semantically, you still need to assemble the word back. Now, my question was that bringing the word down into tokens, does that make a difference to the inference, or it doesn't?
It
Does
doesn't, but it helps when you break down words into tokens, into like sections or parts of a word. It also helps the model understand contextual meaning of the word, because words can mean different things in different contexts. So by breaking it up into tokens, you can create these semantic relationships that could actually even be part of a word. So it's very important factor to be able to decompose these words into small chunks to be able to actually understand language better overall.
okay?
So I want to maybe go one step further, because you hear all this talk around the context windows related to tokens, but I still hear questions on, well, how does a token correlate to a parameter, and what is a parameter, and how do these models actually store its information? So could you give like a real brief description, like how does a token compare to a parameter, or are they one and the same?
Um, they're a bit different. The parameters of the model are essentially weights that the model uses for inferencing. But during the training time, uh, those weights are changed. The value of these weights change depending on the importance of a certain token that is part of the process. So when the model is being trained, it's looking for patterns in these tokens, right? And the parameters of those models, or the weights, are being changed depending on certain patterns that the model has seen through those tokens. So, and then on inferencing time, it actually takes it goes through the neural network, and it basically predicts a word, and then it reassembles basically the tokens and puts them together to be able to predict that word. So that's pretty loaded question. We can spend a lot of time on this, but essentially, that's what happens.
So bottom line, they're not the same.
No,
Parameters are basically just things that will change the way that a model thinks.
that's correct. And tokens basically influence the models, the parameters, the weights of the parameters of the model.
Okay.
So the models, let's say, for example, if I ask the GPT model, right, any of the GPT-4 model, if I say, who founded Microsoft, the Bill Gates and the Paul Allen, their names, the model doesn't need to go to the internet to find that answer. It already knows that answer. That means that is somewhere it has stored that information, um, as probably a relationship, as you're saying, right? The relation between the different parameters. Is that how it is represented? How does that information, that factual information that Bill Gates and Paul Allen co-founded the Microsoft, how is it represented within the model?
Yeah,
Is
and I
it
think
through?
we had discussed this last time, but basically, though there's a correlation to it's part of a it's a complicated question, but it's part of this latent space, right, that you create when you train these models. And that latent space is basically an embedding space that basically takes these tokens and creates these correlations with these tokens or words, and those are represented through the latent space of the model, and the weights determine if like a cat or a dog is closer to each other or not, right? So essentially all that is embedded within the parameters of the model, but the actual information is part of an embedding's latent space. So for the more technical folks on the show here, it's not much different than what we see in traditional retrieval augmentation generation techniques, where we use a vector store, right? The vectors are an embedding space of words and information, and the model uses that actually to be able to correlate back the weight of the parameter back to the latent space to see what that word or relationships of these words refer to.
It's a whole different way of preserving that information. It's not like, just for the folks from traditional world to understand, this is not like a table with the name and the
No.
and the company and the relationship. It is not like that. It's a
Actually
different
a very high dimensional latent space that has over I think the latest models have over 3,000 dimensions of how these words are correlated. So it's how can I say this? 3,000 dimensions is quite a lot to look for. So it's can't necessarily reverse engineering these models to extract the data out of it, because it's part of a very highly dimensional latent space.
That's true. Is that why Sam Altman keeps saying that we really don't understand how these models work?
Well, I mean, it's part of it. Like it's part of it. Like, to me, when I think about parameters and like embeddings, vector spaces that these models use to correlate words, I always say, parameters are important because they determine the size of the model and potentially the complexity of the model. But to me, the dimensions are the most important things, because dimensions represent real things in the world, right? Whether something is an animal or something is a fruit, right? And these dimensions actually provide the definition of what these words are and where they fit within a physical world, right? So when I look at a model's performance, I actually don't even look at the parameters anymore. I look at how many dimensions this model has. That to me represents how intelligent these models are, essentially. When we reach a model that has 1 million dimensions, they're going to be pretty smart.
That's when we hit AGI.
Essentially.
Yeah, or surpass it. Who knows? Yeah. So I've got another question, and it's all kind of interrelated. But I've certainly seen whether it's individuals or companies giving out to their employees, some type of Gen AI tool, whether or not it's something like just ChatGPT or a Microsoft Copilot, or giving somebody something like Gemini and just saying, go at it. 9 times out of 10, that usually fails because no one actually tells somebody how to talk to a large language model, or what's the proper way of talking to a large language model. So we hear the term prompt engineering being thrown around a lot. So I guess my question to you would be, like, why does prompt engineering matter? And how does someone become better at it? And by the way, as you kind of go through your thoughts on that, I'd also be very much interested in what your thought around, is prompt engineering going to be as important as potentially it is today versus maybe 2 years from now? Because I've heard some things like prompt engineering will become less important because these models will be able to help you define the prompt or understand your intent. So anyway, what is it? Why does it matter? And will it still matter?
Sure. Look, I mean, it's no different than when we have a conversation with another human, right? Like, if we don't give proper instruction or we're not clear on the task that we're trying to do, probably not going to get a great response from the person we're talking to, right? So Prompt engineering is very similar. Like, these models, they're masters at language, right? So when they actually use language to communicate with them, which is an interesting paradigm if you think about it. We used to code AI, and now we talk to AI, so it's kind of different. And talking can be very nuanced, right? And so um, when you write prompts, you can really activate certain parts of the latent space of that model to make it do what you want. Okay, there are some research papers that have shown that, for example, if you with certain prompts, you can activate certain parts of the latent space of the model so that they're really good at doing things like in medicine. And you can do that just with a simple prompt. So the prompt actually is what's going to activate parts of the model for you to be able to do a certain task. And therefore, that's why prompt engineering is so important. It allows you to get to a certain part of the neural network and to make the model basically do the task that you're trying to do better. Now, of course, there are other factors to this, like prompt engineering can be used to make the model more deterministic. It could use to make the model ground itself on new data. But prompt engineering is very, very important. In fact, a lot of the work that I do is in prompt engineering and trying to make our customers use prompt engineering techniques to make the models do the task that they're trying to do. At the end, there's a lot of research studies around prompt engineering. And to give you an example, chain of thought was a prompt engineering technique that basically tells the model to think step by step before it executes a task. And just that simple prompt engineering technique, and it's to use it, all you have to do is tell the model to think step by step before it answers the question. And just that increases the model's performance by quite a lot. And so those are known prompt engineering techniques that are so powerful that even companies like OpenAI have used chain of thought inside the training data of the newer models like GPT-4. So now these prompt engineering techniques are actually embedded into the weights of the parameters of the model, and they're much better at doing things when they and when they didn't have chain of thought in it. So to answer your question, will prompt engineering remain? I think it will for a very long time. But what we're seeing is companies that are training these models are actually applying these prompt engineering techniques within the training data so that these models natively have these techniques within the models themselves. A great example of that is like if you look like a GPT instruct model, the word instruct in there actually means that the model was trained on human instructions. And therefore, it's really good at taking an instruction and doing the task that it needs to do on the instruction. That was a kind of a prompt engineering technique that was embedded within the model that makes these models much better at actually responding to instructions. And if you look like a model like ChatGPT, which is old now, but that was one of the first instruct models where the ability for these models to be really good at executing instructions that came from a human actually, are part of the model now. So I think there's an evolution where you'll see prompt engineering techniques being more that are going to be integrated into these models. But I think prompt engineering is still a very powerful technique to get these models to be to do the things that you wanted them to do.
Great.
So these instruct models are trained to be good servants, essentially, right? So
Exactly. Then that's why like ChatGPT was so good, because people could actually talk to them and they would provide good answers, and then like they were able to, and then you can continue a conversation. So yeah, that's exactly it.
how important is that instruct? Do we need to have a instruct model, or with this, more capable models like GPT-4, etc.? Do we really need, or instruct is now kind of redundant?
Yeah, well, instruct models now are de facto on the majority of the models that we see, because it's been so powerful for us to be able to communicate with these models properly and have them do the task that we want them to do. So instruct models basically have been a core component of a lot of the models that you see out there today. And then, there's there's prompt engineering techniques coming out all the time, right? Like there was a new one that came out a couple weeks ago, which is called visualization of thought, which is really interesting. Basically, you tell the model to You tell it that it has a kind of a notepad, okay, and the model can use this notepad to actually visualize certain things. And what that does is it allows the model to actually see what it needs to do, because it actually uses this notepad to like kind of write it down. And then with that, it uses vision to be able to understand what it's trying to do. So in other words, these models kind of have a world space view, and are able to use that to solve even more complex problem. That was a very interesting prompt engineering technique. And so, I mean, if anyone on the podcast here wants to go learn about that, it's a super interesting technique that has proven to increase relevancy of these models by quite a lot.
So I'm assuming that's not how a model becomes multimodal, though, right? Because you just mentioned something like vision and being able to see what it's, reasoning over. But is that what multimodal is? And, how does that differ from just a model's output? So maybe another way of asking it is what you just described. Is that what defines what multimodal is? And is multimodal only concerned about what goes into the model? How does, for this example, how does GPT or ChatGPT output an image? Is that part of multimodal, or is there something else that's going on to interconnect those things?
Right. Well, a model becomes multimodal by integrating the ability to understand and generate content across different types of data, such as text, images, and audio. So a modality actually represents a new perception. Just like humans, we use our eyes, we use our ears and language to make sense of the world around us. LLMs can essentially do the same. By adding multimodal integration, it allows these models to process and produce information in more than just one form. It makes it capable of doing tasks like generating image and sound from text, or vice versa. Now, how can they generate images and sound? The simple answer is that these models, they were trained on a large data set that includes examples of different modalities that are designed to understand and generate different modalities such as images, sound, etc. The training process involves teaching the model to recognize the patterns and relationships between these modalities, which can then be used to perform tasks that involve different types of data, whether it's images, video, or sound, right?
Got it. Thanks.
So other than this, like the text and the vision and the sound, do you think these models also understand the sentiments, intonation, and the pauses and the hesitation? Do they sense those as well? Are they capable of understanding those?
They can. I mean, if you look at kind of a model like GPT-4o, right, it's been trained on audio data and it's been trained on images. So more data you provide these models with, the more patterns it will identify. So if it needs to identify the sound of a car rolling on the street, it will eventually identify that because it's seen it and it was able to create a relationship and a pattern out of it.
Mm.
So kind of want to segue into a different topic relating to models. We hear a lot about, whether it's GPT-4o you just mentioned, or some of the Claude, the Claude 3 models. Those are really large models, under the umbrella of large language models. But we're hearing a lot around the small language models. How do they really differ from a large language model? Is it simply just the amount of tokens that they're created with, or what's the real difference?
Sure, let's talk about that. So an SLM it's a machine learning model that's typically based on a large language model, but it's significantly smaller in size. Now, while an SLM can retain much of the functionalities of an LLM from which it was built from, it still requires far less complexity and computing resources for training and inferencing. And I'll explain why. SLMs, to answer your question, most of the time have fewer parameters compared to the LLMs that we're used to today, like GPT-4, making them a lot less complex and demanding on computing resources. And we'll talk about that as well. But I'll give you an example. Like Microsoft's Phi 3 model uses as few as 3.8 billion parameters, and compared to a cutting edge, LLM like GPT-4 that has over 1 trillion billion parameters, right? So they're significantly very different in sizes. Now, SLMs, I think, are particularly suited for applications where real-time processing or deployment on the edge device may be required, or they're also very good for tasks that demand a very specialized task that can be uh, learned by the SLM using things like fine tuning. It's a very interesting. It's interesting what we're doing with these SLMs now and how we can teach them these really specific narrow tasks by using the overall model itself. They can become really, really, really good at specific tasks. And fine tuning an SLM is much faster and cheaper than an LLM because of its size. So,
So,
yeah, go ahead.
do you think a deployment form factor for the small language models will be phones, or like, I know you're talking about, being able to train really quick, and that could be used for very precise use cases, but is a use case for the small language model disconnected from the internet and run on something like a device?
It could. It could definitely, and I think we're going to see a lot more of that actually. Okay, so let's use another analogy to explain the difference between an SLM and an LLM. Imagine you're in a kitchen trying to make a meal, okay? And a large language model is like having a professional chef, which is fully equipped in your kitchen and is at your disposal at any time. This chef can whip up a very elaborate feast, and it can create these really beautiful dishes because it has all the tools and ingredients they need, and it can handle really complex recipes and serve a very large number of guests if it wanted to. But it takes a lot of space, time, and energy for the chef to be able to do that. On the other hand, an SLM is like having a home cook who uses a smaller kitchen with fewer gadgets, and they may not be able to make these fancy meals as the professional chef, but they can still prepare pretty delicious meals, right? And satisfying dishes that are perfect for everyday dining, right? So they work faster, they use less energy, and they're great for when you need a meal on the table without all the fuss, right? So that's kind of how I see these LLMs. They're the LLMs, are much more powerful, but the SLMs can be just as powerful, but on potentially more simplistic tasks.
So, between the SLM and LLM, does it really matter that there is a definition that how are they being categorized? It seems like they're inherently similar and probably just like a subjective definition of the number of parameters, probably. But is there any hard classification that okay, beyond this it becomes an LLM, or below this it is SLM?
No, not really. I think like at the end of the day, they're all based off typically transformer model architecture. So essentially, they're very similar. I think what changes there is the amount of data that they've been trained on and the size of the parameters that these models have.
Okay. Okay. Cool. So, I think the other question is, since we're talking about this, you talked about this, that the model, um, they have been trained on the images and the sounds and everything. That's why they understand it, and that's why they're able to actually generate those, right? So it becomes a multimodal model. Um, is Do you think that the models, when they are being trained, um, they are being trained on this variety of the media at a go, or is there a different process of training them on the video or audio, or it doesn't matter? Is there a different process of training them on the different media, for say?
Essentially, they kind of go through a similar process, right? Where they get vectorized into an embedding space. So, for example, images, they can be embedded into a vector space. So that doesn't really change, but there are different techniques for these models to be able to understand images or videos better, like techniques like diffusion, where you basically take an image and you throw a lot of noise at it, and then you ask the model to regenerate that image with all that noise. And what that does is it allows the model to have the ability to recreate images. And by doing that a million times, they then have the possibility of generating a brand new image, right? Like DALI. So there are different ways of training these models depending on the modality, but essentially at the end of everything becomes a neural network that has parameters and weights, and the information is vectorized into an embeddings latent space.
Hmm. Perfect. Thank you. I didn't know that.
Yep.
So, uh,
Most models use diffusion to train models, which is what I said, right? Throwing noise at the image and trying to recreate that image. That's the training part of it.
Hmm.
I've got one other question for you, and it's about like where do things stand as it relates to like the future of coding? Because I've even done some things, and I haven't really touched code in like 25 years. That I've been able to very quickly create Python or React code, and it's just been phenomenal. From the things that you've seen, how do you see the future of coding with the advent of these large language models? Is it just going to get better? I mean, what are you seeing, and what do you believe will be happening, I guess, in the future?
That's a good question. I do agree with you. I'm a huge fan of Copilot. It's helped me quite a lot to write code and do demos and all of that. So I think it's the future of coding, with large language models is shaping up to be pretty transformative, in my opinion. It already is. I forget what the stats are, but if you look at the Copilot stat, I think it's 80% of developers that use Copilot today to help them do their work. So in my personal opinion, the future of coding with LLM seems to be one where AI complements the human developers, right? Making coding more accessible, right? Like you and myself, and just makes us more efficient while we still rely on us, to provide creativity and problem solving skills. Let's use the kitchen analogy again, right? Imagine like you're a chef in a kitchen and you had to do everything from chopping vegetables to cooking and planting dishes. Now imagine you have a new kitchen assistant, an AI, right, Copilot, who can take over some of the repetitive tasks like chopping and steering, and so you can focus really on creating like new recipes or presenting, really beautiful dishes. That's kind of how large language LLM models are changing coding. So coding with LLM will be like having a smart kitchen assistant who not only helps with the basic task, but also suggests new flavors combination potentially, and even helps like plate up food in an appealing way. But that doesn't mean that the chef is no longer needed, right? On the contrary, the chef's creativity and expertise becomes even more important. The AI assistant is just there to make the process faster and allow the chef to. It gives the ability for the chef to experiment with new ideas that might have been too time consuming for the chef before because it had to do the chopping and the steering, right? So for coding, it just means that people who write software will have better tools to help them code faster and more efficiently, in my opinion, allowing them to focus on solving even bigger problems and coming up with more innovative ideas. That's my personal opinion.
Yeah, I agree. And I think, we can see some of the stats. Like, I think GitHub CEO says that about 80% of the code will be written by the AI soon. Stack Overflow, right, which is used by the developers, its traffic is down 14% or more ever since the ChatGPT came out. So it clearly indicates that I think the AI is definitely writing more code. But I do feel that the coding is still like an engineering skill, right? I mean, engineering, even though you're not getting into the exact engineering, but the engineering actually teaches you how to think, how to engineer things, right? And then you can transfer that skill. And I feel that the same kind of a building, it's like it's coding is like building, right? You actually learn that process and then you can transfer that to the other thing. And I think Sam Altman also kind of referred to it. I know that there have been some theories around that. Okay, some people say that no more coding required, nobody will code ever, and things like that. But I think Sam Altman also said that it is still going to be a fundamental skill, and he would still recommend people to learn the coding.
I agree.
So yeah, I think the future is definitely going to be different. But I think the LLMs will coexist, do the coding, do the work for us, but they need somebody to tell it to do things. So humans will still be relevant. What else, Simon? Anything else that you would like to add?
No, I think that's what I had. So I mean, thank you so much for having me. I love being on the show, and you guys are doing a great job. I would love to come back and talk about agents, which is the field
Yeah.
I'm on. So
We have to do that.
Definitely
Yeah.
want you back in a future session to go through agents. Looking forward to that one.
awesome,
Yeah,
guys.
definitely. Thank you so much,
Okay.
Simon. Enjoy and
Thanks
talk
again,
soon.
Simon.
Sounds good. Thank you.
Bye bye.